With the thousands of formations sparkling in the firmament, it is difficult to believe, yet there is much to suggest that the Milky Way resides in a particularly empty region of space. In fact, our position in the middle of a gigantic void could turn out to be a stroke of luck. After all, this makes it easier to solve the mystery of the so-called Hubble tension and finally explain why the universe is expanding faster in reality than theoretical models predict. However, this exciting assumption has one small limitation. Strictly speaking, such voids in space shouldn't exist at all. To explain this impossible void, we would need to abandon the established ideas of Einstein and other theorists. There is no room for tolerance or deductions here either. The theoretically determined expansion speed of the cosmos is estimated at around 67 kilometers per megaparsec. However, in reality, the universe is expanding at a speed of 73 kilometers per megaparsec. Since these values seem quite abstract at first glance, we should first clarify what they actually mean and how extreme the deviations between the predicted and observed expansion rates are. The speed at which the universe is currently expanding is expressed as the Hubble constant, and it's no coincidence that the name Hubble is included. Edwin Hubble, the American astronomer in the late 1920s, was one of the first to realize that galaxies in space are moving away from us, meaning the universe is constantly expanding. However, the cosmos is not expanding into existing space. Instead, space itself is constantly growing. As for the unit of the Hubble constant, which might seem unfamiliar, kilometers per second per megaparsec, it's important to note that 1 megaparsec is approximately 3.26 million light-years, and 1 light-year equals about 946 trillion kilometers. For the theoretical Hubble constant, this means that the speed at which galaxies in space move away from each other increases by 67 kms every 326 million light-years. This converts to an expansion rate of 244,000 km per megaparsec. But as mentioned earlier, this is only on paper. When we determine the Hubble constant through direct observations of supernovae, gravitational lenses, variable stars, or red giants, the value jumps to 73 km per megaparsec, or 264,000 km/h per megaparsec. This marks a deviation of no less than 20,000 km/h per megaparsec, making it one of the greatest research puzzles of our time, known as the Hubble tension. But how was this tension confirmed by the James Webb Space Telescope? How could it be that a major cornerstone of the standard cosmological model presents us with such a large puzzle? The simplest explanation would be that past observations were subject to crucial measurement errors that distorted the true value of the Hubble constant. To test this hypothesis, a team led by Nobel Prize-winning physicist Adam Rees from Johns Hopkins University in Baltimore extensively evaluated data collected by the James Webb Telescope over the last 2 years, comparing it with earlier observations. The team analyzed the distances of 16 supernovae, red giants, variable stars, and a special class of carbon-rich giant stars. The result was sobering. The Hubble tension was confirmed once again. More precisely, the new data yielded an expansion velocity of 72.6 km per megaparsec. This result casts doubt on the idea that the deviations from the standard model are due to measurement uncertainties or errors from previous space telescopes. How did the researchers interpret their findings? Adam Rees admitted that our understanding of the cosmos might simply be incomplete. It's possible that we have overlooked something crucial in our cosmological standard model, such as a new component that has given the universe an unexpected impulse after its creation. Alternatively, it's possible that the mysterious dark energy, thought to be the driving force behind the accelerated expansion of the universe, has changed. Other explanations, such as unknown exotic particles, changing electron masses, or certain magnetic fields, are regularly consulted as potential solutions for the Hubble tension. Yet among these many hypotheses, the key to resolving the puzzle could lie in the emptiness of space itself, specifically in the so-called impossible void. With a diameter of 100,000 light-years and an estimated 100 billion stars, the Milky Way is far from being a cosmic wasteland. However, despite its size and activity, Our home galaxy and its surroundings could be located in the middle of a huge, a particularly empty or matter-poor region of space. What is the background of this assumption, and why could it lead to a solution for the Hubble tension? To understand this, we first need to visualize the overarching structure of the cosmos. Stars and planets don't move through space alone. They arrange themselves into galaxies, which in turn come together in galaxy clusters to form superclusters. For a long time, researchers believed that these superclusters were the largest coherent structures in space. However, large-scale surveys have revealed that these superclusters aren't distributed randomly like vegetables in a field. Rather, they are part of a larger, network-like structure. The grids of these superclusters form filaments, long fibers that sometimes span millions of light-years. At the same time, the meshes of this cosmic network also span huge, virtually matter-free bubbles, and this is the key point. Knowing where matter density prevails is crucial for determining the cosmic expansion rate, as this allows for accurate interpretation of corresponding measurements. A research group led by Ben Hite from the University of Wisconsin-Madison discovered several years ago that there are indications of a relative void around the Milky Way and its surroundings. Spectroscopic surveys of space revealed that we may be in a void that extends over 1 billion light-years, 7 times larger than what would be expected for such empty areas. Recently, experts from the University of Bonn and the University of St. Andrews made similar observations, lending further support to the void theory. To illustrate this, experts compare our position in space to a bubble in a cake. Around this bubble, the density of matter is higher. Conversely, this means that gravitational forces emanate from this surrounding matter, pulling galaxies inside the bubble toward the edge of the cavity. This causes them to move away from us faster than would be expected. The mysterious deviations of the Hubble constant, which have puzzled researchers for so long, could therefore be explained by such a local underdensity. In fact, another team of astronomers recently evaluated the average speed of galaxies located 600 million light-years away from us and found that these distant star systems are moving away from us 4 times faster than the standard model of cosmology predicts. And the reason is as simple as it is profound. According to established theories, such underdense regions should not exist at all. Why is this so? The fact that cosmic voids are theoretically impossible is rooted in the assumption that matter should be uniformly distributed in space on large scales, not concentrated in clumps surrounded by empty bubbles. Yet, according to the study authors, we should not forget that our standard model is based on Einstein's theory of gravity. What if Einstein's theory is incorrect? What if gravity behaves quite differently than we have assumed? This is where the modified theory of gravity comes in, known as modified Newtonian dynamics, MOND. Proposed in 1983 by Israeli physicist Mordechai Milgram, MOND offers an alternative to dark energy by explaining the rotational behavior of galaxies through modifications to the equations of motion in the gravitational field without invoking dark energy. Though MOND remains a debated theory and has not gained widespread acceptance, it predicts the existence of vast, empty bubbles in space. Furthermore, if MOND's predictions hold true, the problem of the Hubble tension would disappear, as the observed discrepancies would simply be due to irregularities in matter distribution. However, this would also require abandoning some fundamental assumptions of Newtonian gravity and Einstein's general theory of relativity. Whether this outsider theory will hold up against established models remains to be seen. And with that, don't forget to hit the thumbs up and subscribe to stay up to date with our latest videos. We'll see you soon.